The previous couple of lectures, we started to define the system in terms of the wave function given as a superposition of states. And as we went forward, we also tried to understand what will be the expectation value for a given measurable, which is given by the trace of the product between the projection matrix and the operator matrix. And as we also introduced the ensemble averaging, we were able to say this projection matrix gets rewritten as the density matrix. And we also derived the Liouville von Neumann equation, where the evolution of density matrix as a function of time is given by the commutator minus I times Hamiltonian comma the density matrix. And we said if Hamiltonian is time independent, then the solution is given as sigma of t will be given as exp minus iht sigma of 0 times exp iht. And we also expanded this in terms of the Baker-Campbell-Hausdorff formula, where sigma of t will be given by sigma of 0 minus a Taylor series expansion that looks something like this. In today's class, we will be furthering this concept and we will try to understand what if the Hamiltonian is time dependent. In the case that the Hamiltonian is time dependent, we will resort to a method where we will do a similarity transformation to the density matrix such that you would have a unitary operator U that is operated on the density matrix, where the Hamiltonian becomes time independent. Because the moment you make the Hamiltonian time independent, then you can apply the BCH formula. So that makes our life easy. We will be working out a formalism right now, how this unitary transformation, or the similarity transformation that we have listed here, would help us achieve this target. So just to give an idea of what is a unitary operator, we have seen different types of relationships between matrices, symmetric matrix, skew symmetric matrix, Hermitian matrix, and so on. A unitary matrix is one where the U inverse will be given by its adjoint. Meaning, generally you know that U inverse will be given as the identity, and in this case, this will be equal to U adjoint. So of course, this implies that the adjoint and the inverse are one and the same. By adjoint, I mean transpose and complex conjugate. So we started with sigma and the Hamiltonian, where this Hamiltonian is time dependent, and we did a unitary transformation with the operator U such that sigma becomes sigma of R. So now let us ask this question: how will the Liouville von Neumann equation can be rewritten for this transformed density matrix? This is going to be given by d over dt of U sigma U inverse. Since it's a differential involving three variables, you have to carefully do it. Du by dt, and we know for a fact this is what was given by I times sigma comma h. This is what we have seen earlier as the Liouville von Neumann equation. And in addition, what I'll be doing here is that I'll be inserting here a U inverse U, since that will be equal to identity. This can be done. And similarly here, I'm going to be introducing a U inverse U. We will see why we would do this to make our life easy. So d sigma r over dt will now be given by du by dt U inverse U sigma U inverse. As I said, this will be equal to identity, so therefore we can multiply anything by 1. U times I sigma comma h U inverse plus U sigma U inverse U du inverse dt. We have done this so that you are able to get the U sigma U inverse term here, which can be represented as sigma r. So therefore, this is going to become du by dt U inverse sigma r. I'm going to end up moving the last term. Once again, you have plus sigma r u du inverse dt plus ui sigma Hamiltonian u inverse. So now what has to happen is that we are able to see these two terms look quite similar to each other. We'll also quickly invoke a basic thing, that is u inverse is equal to E, therefore differential of it with respect to time du by dt times u inverse, u du inverse by dt is equal to 0. So this implies we can write one of them with a negative sign. So this can be written as minus u du inverse by dt sigma r plus sigma r u du inverse by dt plus, I'm going to take the u inside, so therefore you're going to get inverse comma u Hamiltonian u inverse. And if you pay close attention, you are able to see this is nothing but the commutator between sigma r comma u du inverse over dt plus I times sigma r u Hamiltonian u inverse. So now what have we done? We have successfully written what will be the time evolution of the transformed density matrix, and this equation looks kind of similar to the Liouville von Neumann equation. So now what we can end up doing here, we can rewrite this as I can be taken out as sigma r comma u du inverse over dt. Since I was not present here, need to put a minus I, since minus I square will be equal to plus 1, and then sigma r has come out here, so here I would be present, so you're going to have u. Let me rewrite it so that you are able to appreciate what we have gotten finally. This equation looks very similar to the Liouville von Neumann equation you had gotten earlier in the previous lecture. The only difference being, now that you have transformed sigma into sigma r, it has happened uniformly here, and our new Hamiltonian, which is h prime, will be given by u Hamiltonian u inverse minus I times u times du inverse by dt. So now what we have achieved, if we are able to find a unitary transformation such that the Hamiltonian can be made time independent, you are able to come back to a very similar equation wherein d sigma r by dt will be given by I sigma r comma h prime, where the h prime is given by u h u inverse minus I u du inverse by dt. So this is an important relation. So once you have achieved this one, and you also made the Hamiltonian time independent, now you can jolly well repeat what you had done earlier, where you can write the solution as given here. Let us recap what we have seen so far. We had represented the system in form of a wave function, and to predict a given observable, we get the expectation value, which can be determined by the trace of the density operator to that of the operator itself. Where you get the trace, you will be able to predict whether, if it's a non-zero or a zero trace. If you get a zero trace, it's not observable. If you get a non-zero trace, it becomes observable. And we also derived the Liouville von Neumann equation. Therefore, we resorted to a similarity transformation where the density matrix is transformed with a unitary matrix U. And here what we were able to achieve is that once you deduced it, you are able to arrive at an equation where T sigma r over dt will be given by sigma r comma h prime, where this h prime would be u h u inverse minus I u du inverse by dt. Meaning that if you are able to find a unitary transformation which can make the Hamiltonian time independent, then once again we come back to a Liouville von Neumann equation, which looks like what we had started with, and therefore we should be able to apply whatever we had deduced earlier. This being the premise, you will be taking an example where, similar to what you had done before for the bulk magnetization, you will be going to something like a rotating frame. We will be developing a similar formalism in the quantum world as well. And in order to do this, I would request you to recollect the fact that in order to go to the rotating frame, you ended up precessing along the z-axis with respect to the transmitter frequency. So therefore, the choice of the unitary matrix that we would end up picking here would be given by exp I omega r of t along the z-axis, where omega r of t is the angular frequency. If we have to find how does the Hamiltonian change, we need to first write the Hamiltonian, and we will just take it for a simple isolated one spin half system where you are also applying an RF pulse. And if we might remember, we wrote the chemical shift Hamiltonian as omega naught Iz. To be precise, it should be minus sigma times omega naught Iz, where sigma here indicates a shielding variable, but here I'm not going to introduce it for the sake of simplicity. So we can just say it's omega naught Iz plus that of the RF pulse. So we had deduced that the RF pulse will be given by B1 cos omega r of t plus phi times I cap plus B1 sin omega r of t plus phi j cap. So similarly, since I've already multiplied it with the minus gamma, I'm going to write it directly omega 1 cos omega r of t plus phi. So in order to see whether this unitary transformation makes our Hamiltonian time independent, what we have to do is to see what happens when we apply the unitary transformation on the Hamiltonian. And as you are able to see the second part, this doesn't have the Hamiltonian, so this might be easier to start with. So I'm going to be deducing the second part of this, so therefore minus I, u is given by times exp I omega r of t times Iz, time differential of the inverse of this operator. Inverse of this would also have a complex conjugate, exp minus I omega r of t Iz. So what will this be? Minus I times exp I omega r of t Iz. Time differential would end up picking minus I omega r of Iz times the function back, since it's an exponential function. And you are able to immediately observe these are inverses of one another, so therefore you're going to end up getting 1. And you have minus of a minus, which is going to be plus I square, which will be minus 1. Therefore, you're going to end up getting minus omega r of Iz. Okay, so we are done with the second part. Now we'll go to the first part. The first part can also be divided into the chemical shift and the R of Hamiltonians. Let's try to do the chemical shift Hamiltonian, the transformation for the chemical shift Hamiltonian, which will have UHCS U inverse. If you are able to see here, you are going to get exp I omega r of t Iz omega naught Iz exp minus I omega r of t Iz. This will result in a commutator Iz comma Iz if you recollect the BCH formula. Since Iz comma Iz will be 0, what will end up happening? This term will appear as this. So therefore, H prime will have an omega naught times Iz. And remember that the second term has resulted in minus omega Rf times Iz. So I'm just going to combine both of this in one shot. This will be omega naught minus omega Rf times Iz. If you might recollect, omega naught minus omega Rf is nothing but the offset. So now what you are left with is the transformation of UHRF times U inverse. So where we will call this the HRF. So this will be dealt separately because this is a little involved calculation. So I have rewritten whatever solutions we got, where we have taken the chemical shift Hamiltonian and the second part, which is minus IU du inverse by dt, has been written directly as capital omega times Iz. This is the only transformation we need to do, where the Hamiltonian for HRF is given by. So now this also I'm going to be dividing into two terms. Let's take the Ix term separately and the Iy term separately so that it becomes easy for you. So for now I'm going to be writing only this part. So let's write. So this looks very similar to us where we had can write the solution in the expansion of the BCH formula. We are exactly going to do it right now where for this sake we have set Hamiltonian as minus omega RF times Iz. Why does the minus come up? Because you have a minus here and you do not have a minus here, and therefore we are setting the Hamiltonian to something like this. So we are only going to be seeing the first part of it. So this will be given by Ix minus IT over 1 factorial Hamiltonian, which is minus omega RF times Iz comma Ix So let's do it one step at a time. You would understand that this would end up becoming minus omega RF times Iy. So therefore, I'm just going to borrow it here, minus omega RF times Iy. So what will be the commutator of these two? That will be equal to minus of a minus would become plus omega RF square. Iz comma Iy would be minus Ix. So therefore, minus I square Ix. So similarly, this one is, so therefore this is going to be minus omega RF square Ix. Because you're going to have a minus 1 square, there will be plus 1, minus I square will be minus 1. Therefore, you can get this, and the entire thing will therefore be so let us simplify this now. Ix minus, you see a minus of a minus, that should become plus, and then you have an I square, that will once again make it a minus, so therefore minus will remain. I'm going to end up writing omega RF t power 1 by 1 factorial times Iy. The second term has only Ix in it, minus omega RF times t the whole square divided by 2 factorial times Ix plus omega RF t the whole cube by 3 factorial Iy and so on. I request you guys to calculate the other terms. So this is going to be nothing but, if you take Ix outside, you're going to have 1 minus omega RF t the whole square by 2 factorial plus omega RF t power 4 by 4 factorial and so on, minus Iy omega RF t by 1 factorial minus omega RF t the whole cube by 3 factorial plus omega RF t power 5 by 5 factorial and so on. You are able to appreciate the fact that if omega RF t is set to theta, you have something like 1 minus theta square by 2 factorial plus theta power 4 by 4 factorial and so on. Here you have theta minus theta cube by 3 factorial plus theta power 5 by 5 factorial and so on. This is nothing but the cos series, so you're going to get Ix of cos, what is theta here? Omega RF t minus Iy sine omega RF t. So whatever we have done so far is just looking at the first term here. If you repeat the calculation for the second term, which I strongly urge you guys to do, I'll write the solution directly for this. The second term, because this had a multiplication with cos omega RF t plus phi, then you had a sine part plus Iy cos omega RF t plus Ix sine omega RF t times sine of omega RF t plus phi. You have almost come to the conclusion here, where remember you're talking about the transformed Hamiltonian, and that also included omega iz plus the whole thing. So if we try to expand it, you are able to appreciate the fact that you have an ix cos, let's say this is alpha and this is beta. You have cos alpha cos beta plus sin alpha sin beta. If you carefully do the arithmetic, you are going to end up getting ix cos of omega rf t plus phi minus omega rf, because you have cos alpha cos beta plus sin alpha sin beta. So that's going to be cos of alpha minus beta. And if you do the same thing for iy, you're going to be looking at sin of omega rf t plus phi minus omega rf. So what this has effectively achieved is remove the time factor in the Hamiltonian. Therefore, your transferred Hamiltonian will be just given by the offset with iz. I also missed an omega 1 factor everywhere. Omega 1 ix plus omega 1 omega, get omega 1 ix cos phi plus omega 1 iy sin phi. Capital omega is the offset. You are now able to see there is no time dependence on this Hamiltonian. Therefore, we can happily apply the Liouville von Neumann equation, where you would be able to get the solution in no time. So we will be able to apply the Liouville von Neumann equation, especially the solution to it, where sigma r would be given by exp minus I h prime t times sigma 0 of r times exp plus I h prime t. I hope this exercise has been useful for you to understand. The moment you go from the lap frame to the rotating frame, you are able to see the time part of the Hamiltonian is completely removed. Of course, we are not discussing the aspect where omega 1 could be time dependent, or even the phase could be time dependent. All that we have said so far is that the transmitter frequency can be nicely negated when you end up going to this transformation frame. For now, it suffices the fact, if you do a similarity transformation, you will be able to go to a solution where, if you know the initial density matrix in this transform frame, you'll be able to say what is the final density matrix. If you're able to say what is the final density matrix, then you would be able to predict whether a given measurable can be obtained or not. In the next lecture, we will be looking at how the equilibrium density matrix sigma of 0 can be written.